And welcome back. Now this week, have we in fact got the ultimate Rotary Encoder debouncer circuit here? Yes, not a software debounce in sight, this is all done by hardware, and it's a lot simpler than what this mess of cables and capacitors and whatever would have you believe. Yeah, let's have a very quick look at this, and I promise never to mention rotary encoders again. Well, not until the next time anyway. Yes indeed. Now, since we last spoke about rotary encoders, and I used that state check thing that said this is an impossible state, so I'll remove it, but you could turn the rotary encoder and it would always be correct because it knew the state of what the switches had to be in. Fine, okay, and there were lots of comments on that, of course, not unsurprisingly. And I thought, hang on a minute, I've been down this road before when I used a hardware solution. And I looked back on my videos and it's very old now. And I thought, you know, now's the time maybe to rethink it and do it again. This time perhaps with a PCB and everything. So what I've done is put this little tiny circuit up here, and I say straight off the bat, this is not my circuit. This is the circuit that Jack Gansler proposed in his paper about debouncing. He goes, this circuit works in all cases. So, well, first of all, let's have a very quick look at what happens when I turn that rotary encoder. I've got a little serial monitor hooked up, so you can just see it working. And then we'll have a look at the circuit, I think. That's the best thing. Now, a quick shout out to my sponsor, JLC PCB. They're doing a collaboration with EasyEDA. As you know, it's my preferred PCB CAD program. It's simple but powerful. It's intuitive to use. Let's just have a quick look at a design I made recently. So here's a fairly recent design of mine, my ESP32 web radio. Designed it in EasyEDA because it had all the features that I needed. And don't forget the teardrop feature that allows the tracks to be slightly bigger at the ends where they join pins and things to give them a bit more stability. And then you just click the Gerber button at the top here. So that one there. And it says, great, you can either generate your Gerber files directly or order them at JLC PCB. And if you click that, it will go straight to the JLC PCB site, upload the Gerber files as it's generating them in the background automatically, and show you what you can do there. And let's not forget, they got a Facebook group. Here it is. And as you can see, they're joining forces here a bit more transparently, so we understand that the two are connected. EasyEDA to design your PCB and JLC PCB to actually manufacture it. Sounds good to me. And if you join the group, there's all sorts of good things on the way, so have a look at that as well. JLC PCB, go and have a look. Okay, I've got the debug window there sitting there, and I've pushed the rotary encoder button down once just to say, look, it says reset to 0, just something I'm doing. So if I turn this now to the right, you'll see that yes, it goes up to the right. And if I turn it to the anti-clockwise to the left, it says yes, you're going to the left. Okay, and that's counting. But there's something I discovered whilst doing this that was one of those eureka moments. It was like, oh, why didn't somebody tell me about this? Because this is a Bourns rotary encoder, yeah, and I bought it from RS Components because I thought, well, how can I put this delicately? I wanted something that was of reasonable quality, and I'm hoping that RS Components buys stuff that they've tested out and go, this is of reasonable quality, we'll buy it and put it into our catalogue. Okay, so that's from RS Components. It's almost undoubtedly manufactured in the Far East, but that's not the point. It's manufactured, one hopes, to a standard. Okay. I mean, let's face it, Apple iPhones are built over in the Far East as well, and they're all manufactured to a standard. So I think we're on a winner. Having used this during my experiments, doing pretty much what I'm doing here and playing about with some of the values here, I found this happens. Look, if I turn this very fast, too fast in fact, oh, here it says it, look, too fast. Yeah, okay, I've put that in the code now because when I looked at the data sheet for this particular rotary encoder, and most mechanical rotary encoders are the same, the maximum RPM is 60 RPM. Now that doesn't mean you can whiz this round at a rate of knots until you get to one click from the 360 degrees and then wait a bit and then click it that final one and go, oh, I only turned it at 60 RPM. No, this is more like an average speed camera you find on the roads. Yeah, you've got to turn this no faster than the equivalent of 60 RPM. Which explains, I think, in some ways, why the rotary encoder in my car, which is a volume control and a tuning knob as well, if I turn those too fast, nothing happens at all. Nothing. So I want to turn the volume up real quick, and I turn it, nothing happens. The volume does not change. If I do it reasonably slowly, then it goes up and back down again. But a fast turn does nothing. Exactly what I've now had to do on here. And I thought, why is this? I've investigated a bit. Basically, the mechanical restraints within this rotary encoder are such that if you turn it faster than that, apart from the severe wear you'd get, of course, spinning it very fast, they can no longer guarantee the integrity of those wipers. Yeah, there's two pins on here, as you know, pin A and pin B, and they're out of phase by 90 degrees. So as one goes high, the other one stays low for a bit and then goes high later, which is how we can detect which direction we're turning this knob in. They say if you turn it faster than that, we just cannot guarantee what's happening inside that pot anymore, as it's wiping the back surface, a bit like a potentiometer does. Yeah, the wiper touches a track, doesn't it, on the back? Well, this does the same, except the track is chopped up into little bits, so it hits a bit of the track and then nothing, and then another bit of the track and then nothing, and so on. Yeah, rather than actual switches, like you might find, say, in a toggle switch. Again, when you spin it that fast, these wiper things just behave erratically. You just cannot control them anymore. And this isn't switch bounce. Well, it might be related to switch bounce, but it's just the mechanical inertia and the fact that you're overdriving this now. After all, can you rev your normal petrol engine in your car to 10,000 RPM? No, of course you can't. Not unless you've got something. All right, yeah, okay. Some motorbike engines do go that high, but I'm talking about a car, 4-cylinder car. No, of course you can't rev it to 10,000 RPM. Why not? If you can rev it to 4,000 or 5,000, why can't you then go to 10,000? Well, we all know the answer. I mean, the things that just go absolutely haywire. It can't cope with that speed. The valves will be shooting through the pistons and everything else, right? Which is why petrol engines are limited. In exactly the same way that this is limited to 60 RPM. Now, 60 RPM is one revolution from where it is now. You can see it's at the 12 o'clock position, yeah? So that means from there all the way round back then has got to be done in a maximum of 1 second. And I've been looking at the output on this screen here to make sure I don't turn it in more than 1 second, and it's very easy to do. 1 RPM is in fact quite slow, pretty much about what my car accepts. So who knows, in my car there might well be one of these. So not only are we looking at switch bounce elimination, we're also saying you just cannot turn these that fast and expect to get a sensible output. So what I've done then is construct this circuit from Jack Gansler, and it absolutely guarantees no switch bounce. So we'll have a look at the circuit. But as well as that, in the software, I've had to say, fine, give me all the interrupts you're going to give me, but if I discover you're sending me pulses too quickly, I'm going to say, no, I'm doing nothing with that. I'm just ignoring it, because that's the manufacturer's specification on here. It cannot guarantee what is being output anymore. Fine, let's have a look at the circuit. Right, this is the schematic of the entire thing, and it's just 3 bits repeated, which you can actually see. If I get my mouse on there, it says 1 bit here, 1 bit here, 1 bit here, and they're all identical. And they're all this. So let's zoom in on this circuit. There we are. So this is, as I say, Jack Gansler's circuit from, well, 2004 initially, and he revised it a couple of times. Well, the document, not necessarily the circuit. So how does this work? Well, the switch, the rotary encoder switch, is connected between ground on one pin, say pin, well, it's the center pin actually, and then you've got pin A here, but what do you do with pin B? Well, you have an identical circuit, and pin B is connected to the same place, but in a different circuit, okay? So what's happening is here, this is VCC up here. Current comes through here, let's forget the diode for a minute, comes through R2 and charges up this capacitor. And there's lots of maths in Jack Gansler's document, but he hints at the right values. And I'm using 82K here and 18k there, and 0.1 microfarad capacitor there. Easy values to find, pretty much. And he says, you know, it's a bit finger in the air job, although the maths is very specific. Close enough is close enough. So this capacitor here gets charged up when the switch is open. Great. It's okay. So we turn the rotary encoder or flick the toggle switch or whatever it is we're doing. Yeah. So this now connects this point here to ground. So at that point, the capacitor no longer is being charged, but in fact it discharges via R2. And when it discharges enough, it goes below the critical threshold here, and this Schmidt trigger goes from one state to another, just like that. Okay, there's no intermediate state like a transistor would be, for example. You know, we have this linear region, none of that. It just goes from low to high or high to low. And that little dot at the end there, that circle, means it is inverting. So what if it's high here, it'll be low here and vice versa. Doesn't matter to us at all. So this capacitor discharges, gets to a certain point, the Schmidt trigger flips, and you have your very clean pulse. No if, buts or maybes. So why all this bit then? Well, imagine that you flip the switch here, so it closes, capacitor starts discharging, but it's not yet low enough for this to flip. But switch bounce then causes it to open and close a couple of times. So what happens? Well, every time this opens, the capacitor can get recharged again, of course, just that little bit. But the point that is very important is that this pin here on the Schmidt trigger stays at its previous high level. It hasn't dropped low enough yet to trigger. So it bounces a couple of times, but the value here is still high. And eventually, of course, it closes properly, the capacitor discharges, bang, the output changes. Now, Jack Gansler says sometimes the maths breaks down a little bit and R2 gets in the way of this charging mechanism. So by effectively shorting out R2 with this diode, and I've used a Schottky diode, so the voltage drop is just 0.2 volts, the charge path is really down here through the diode and into the capacitor. But of course, when the capacitor discharges, it can't go backwards through the diode, so it has to go through the resistor. So it's a slow, relative term here, a slow discharge, yes, to give it a chance to discharge properly with whatever switch bounce is going on here. I suggest you really do read the paper. Just flick through the bits and watch the pictures if you like, because I mean I saw the maths and I thought, oh God, maths is not my strong point. But I understood what he was trying to say, and I thought, great, just give me some figures. But he's very cagey about the figures. But the two that he eventually gives out work well in this instance. So if we just zoom back out here, you can see that what I've done. Let me just get rid of this side as well. So this is the rotary encoder, the Bourns rotary encoder, right? We got 3 of these circuits, 1, 2, 3, all identical. One's for the push switch, the bit I said where it resets to 0, and that's pin B and that's pin A. So the rotary encoder is connected at these points here, but the output from this circuit, basically this point here, is connected into the Schmidt trigger. And there are some unused gates here, and we have to bring those low. Now, just one little word on that. If you thought, oh, I don't like the idea that if it's low here, it's high there, and vice versa, we could put the output of this into one of these unused gates. There are 3, look. So funnily enough, you could put the output of one of these into the input of another to invert it back again. So it would be high input, high output. I haven't bothered because I just wanted to see how it worked, but it's always an option. And that is the circuit. I mean, there's nothing else to it. There's the connectors really in and out that you find on any rotary encoder module. VCC, ground, and then the 3 pins, pin A, pin B, and the switch. Great. Now, I've designed but not yet received a PCB for this, which looks a bit like this. If I go up here. Right, there we are. That's the PCB. Now, it looks huge, but it's not. It's quite small. In fact, if I switch on the document, we might. Yeah. So 43mm long, and you can't see the bit at the top because all this other stuff. 29.7 millimeters wide, it says there. Yes, and I have panelized this because when you create PCBs or order PCBs, you're allowed up to 100 by 100 mil at the same price. Yeah, so I thought, well, how many of these can I fit into 100 mil? The answer is 6. So if I order 5 PCBs, which is the whole thing, 5 times 6 is 21. I told you I was no good at that. Now, you get 30 of these panels, right? Which means I'm going to have some left over. Yeah. Okay, so let's have a look at the 3D version of this thing, because I think it probably gives you a better idea than just this. 3D, let's have a look. There it is, populate with all the components. So there's the rotary encoder, the chip goes in here, and all these capacitors and resistor pairs and the diodes and all that are just that bit of the circuit by Jack Ansler. Okay, so I reckon that'll be good enough. Now you might say, why oh why, Ralph, didn't you make this with surface mount components? And believe me, I was going to. If I make it surface mount, anybody else wanting to construct this could have barriers, yeah, to that construction. I know that surface mount construction is not for everybody, so I thought, well, let's just make it easy for everybody. We'll have through-hole components first, and should somebody want to make this into a surface mount one, you can make it probably half that size, I would imagine. I mean, look at the size of these resistors. Yeah, even though that's a 1/4 watt resistor, a surface mount resistor is going to be, 1/10 of that size, isn't it? And ditto with all the capacitors. But anyway, I think this is good enough to try it out on. Yeah, and that circuit that you see here, or this board that you can see here, is exactly what we're looking at on my workbench here. That's what all that is. Yeah, a little bit messy, but that's. Oh, reset to 0. Look, that keeps coming out of its little sockets. Cool. Okay. Right. Couple of other things to cover then. Right, sorry to interrupt the main video. This is recorded after that video because the PCBs have arrived, and I've just put one together real quick. And he arrived about an hour ago, so I quickly whipped in those components, and yeah, it looks all right, doesn't it? The addition to what I made from the one you saw previously is that I also added the LED and obviously the dropping resistor, because there's nothing worse than connecting something up, nothing happens, or it doesn't work, and you think, is there power on here? And the only way to find out is then to put your multimeter on it. So I thought, you know what? I'll put an LED on here just so that we can see that it is powered up, because you can always remove it or not fit it, as the case may be, right? Okay, time to bring up the IDE window that I was using for this. What was I using? Oh yes, I was using CoolTerm for this. Let me bring this up just over there. Okay, there we are. That's the window, and as you can see, I've been playing about a bit. So let's reset that to 0, and we can turn it right, and we can turn it left and right, and it all works. And of course, if you go too fast, it says it's too fast. In real life, what happens when it says too fast? It just ignores that pulse until it gets one within the right time scale, as talked about in this video. Okay, so the PCBs look like this. So this is in fact a panelized, well, part panelized board. I've already taken 2 off. Yeah, so they're pretty small. They've only got this little tiny margin between them that comes off nice and clean because they're all V-cut. Yeah, so I've got however many it was I said. Did I say 30? Well, I've used 1. I'll probably keep another 2 or 3 for myself. And that's it. So look out for a pinned comment in the video description below, because that will tell you whether I've got any of these left or whether they've all been snaffled. Okay, and it doesn't matter if it's a week after this video or 2 years after this video. Sometimes people just are not interested, and I have these PCBs for a long time afterwards, and gradually people take them on. Okay, that's it. Back to the main video. Well, let's have another look at this rather gorgeous little PCB, and yeah, lovely. I must admit I'm quite pleased with that. I know it's a simple PCB, but things can still go wrong, you know. Cool. Okay, back. Now, while I was trying all this out, obviously I was trying to get some switch bounce so I could prove that it was working. And it was harder than you might think. Sometimes it would, sometimes it wouldn't. I thought, there's no way I can do this live in a video because I'll be here forever trying to get the switch bounce. So I thought, what I'll do is take some pictures as I'm doing it. So here's a picture. Now this is the worst switch bounce that I've ever recorded while I was doing all these experiments. It never was this bad normally, but as you can see here, the number of times this goes up and down, and then not even all the way down to ground, like it just bounces about and eventually settles. That is a good example of what, well, bad switch bounce is. Yeah, let me show you another one. Okay, now this one shows both input and output. So the rotary encoder at the top here was turned and it went to ground, but then bounced about here just for a fraction of a second. So with 500 microseconds here, look, per division. So that was pretty quick, but not quick enough for your microcontroller not to detect that under normal circumstances. So you get the switch bound output, something we definitely don't want. And then a few microseconds later, we have the clean switched output here with no bounce at all, this is why I took the photo, because this is an excellent example of the rotary encoder, yes, coming to ground but bouncing about a bit, but then a few microseconds later, the output going high, nice and clean. Not bad, yeah? I think there might be one more picture I can show you. Yes, this was an interesting picture. I thought, was that switch bounce or is that something else? Is that just noise? So the rotary encoder was turned, it went to ground, and then we had all this bouncing about for quite a long time, given that it's 100 microseconds per division now. So for, probably half a millisecond, all this was going on. And I don't really know whether that was switch bounce or something else. It could very well be switch bounce. And then it settled down after that. There was no more noise or switch bounce or anything else. But what this showed me is that switch bounce, try saying that 10 times quickly, is one of those insidious things that you can't always, well, I was going to say depend on. You don't want to depend on it, but what I'm saying is it's not always there. Sometimes it will, sometimes it won't. It depends on how hard you turn something or flick a switch or whatever. Some switches do it all the time, some switches hardly ever do it, but the hardly ever is not really good enough, is it? Hardly ever means occasionally you'll get a switch bounce, which means you'll have more than one pulse given out, which might mean whatever you're pressing is doing something more than you should. In fact, my telly, the remote control works well enough 99% of the time, but sometimes you press a button for the change of the channel and you get the number 4 come up twice, for example. You think, well, I only pressed it once, why has it gone 4-4? And then, of course, you're stuck. You have to put another number in to make it go around the loop again. I know. So switch bounce is one of those things you do want to get rid of. And the good thing about this is that the hardware solution, takes up no time in the software, apart from the I'm not accepting any silly speed you're turning it at. All the switch debouncing is doing here. So the stuff coming into here via those coloured cables at the back, they are clean, pristine, square waves, and you can depend on those through the addition of this very cheap and simple hardware solution. I think that's it. I think I've covered everything I'm going to cover now in rotary encoders. Yeah, I know. Until the next time. But if anybody wants one of those PCBs, assuming that I've got them and they're all there, I'll put a notice up, both on the comments down below. I'll have a pinned comment down there to say whether I've got any. And I'll send them off, because obviously I only want 2 or 3 here for me. But if I'm going to make all these, I might as well spread them around, and you can source these components, which are cheap and plentiful, and there's only about 6 on there, wasn't there? It's not a lot, and then you can play with it yourself and see what you get. Okay, right, I think we're done here with the rotary encoders. If there's anything else that I need to tell you, I'll put it into the video description below. Do have a read down there, and don't forget the GitHub, because I'll put the sketch that I'm using on this ESP, but it'll work on the Arduino the same, just got to change the pin numbers. And of course the circuit for this and the PCB and all that I'll put up there on the GitHub as well. But remember, I may have some spares. Well, almost definitely will. Cool. Okay, thanks very much for watching. Don't forget to like this video if you did, and comment down below, and I'll see you next time. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.